Welcome to Chem 1A at Shasta College. This is a screencast on some of the mathematical material in the first chapter, dealing with ideas like measurement, significant figures, and dimensional analysis or conversion between units. And let's start with a question. How far do you travel, or in this case, how far does Racer Ralph travel to get to school? Well, let's say that he travels 17 miles. Notice that this is an example of what's called a physical quantity. It has both a number, the 17, and a unit, the miles. And when we measure things, that's typically going to be the case. Physical quantities will have both a quantity and a unit that pertains to that quantity. Now, we typically use metric or SI, Système International des Unités, units. And the basic units in the SI system are meters for length, kilograms for mass, Kelvin for temperature, seconds for time, moles for amount of substance, amperes for electric current, and candela for luminous intensity. Some of these we will use quite a bit during the semester. Others, like let's say luminous intensity, probably never experienced in your chemistry class. It's a good idea to start getting familiar with the units and their abbreviations as well. Now, a second example is how much water do you think there is in the total volume of the Earth's oceans? Well, you can certainly predict it's going to be a pretty big number, and it turns out to be approximately 1,300,000,000,000,000,000,000,000,000,000 liters. That's a pretty big number, kind of cumbersome to write, and of course many of you will be noting that writing it in scientific notation, or 1.3 times 10 to the 21st liters, would be a much more compact, much easier way to write this. So we often use scientific notation for very big numbers. And on the flip side, how about the diameter of a hydrogen atom? Well, you probably know that hydrogen atoms are very small, have a very small diameter. Turns out that that's approximately 0.00000000074 meters. And this is, again, kind of cumbersome to write all those zeros, easy to miss one. But we can write this in scientific notation as 7.4 times 10 to the minus 11th meters. Note again the importance of adding the unit to your value, and hopefully you've been exposed to scientific notation before, and if you're a little rusty on it, make sure that you get it all squared away or ask for help if needed. Now, a little more background information. A lot of times if we have really big amounts or really small amounts, we use prefixes like mega, kilo, deci, centi, which are a million, 1,000, 0.1, 0.01 respectively, and then milli, 0.001, micro, 0.000001, or a millionth, and nano is a billionth. There are, of course, other prefixes, but these are probably the most common ones, and it would be a good idea to get familiar with those. You'll be expected to know what milli or micro or kilo or centi mean. Now, how about a few more examples of physical measurements and or physical quantities? And in this case, let's take a simple example. How much does a candy bar weigh? What's its mass? And how do we determine it? Well, hopefully you'd say, pretty simple. Put the candy bar on a balance or a scale. This is an old triple beam balance. We'll typically in lab use electronic balances, and these are pretty easy. You zero or tear them, and then the weight is just given on the readout. And in this case, it says the candy bar weighs 104.987 grams, and you will record that whole number if this is something you're actually asked to determine. So that's going to be, you would write out 104.987 grams, not 105 typically. You always have the right to reduce the precision of this if you're going to do some sort of approximation later. But if it's measured very accurately, you might as well write down the number very accurately. Now here's another example. How long is this paperclip, and how do we determine its length? Well, hopefully you would say, let's use a ruler. And it is important to note that you're going to want to line up the ruler very carefully, have a reference point on the ruler that corresponds to one end of the paperclip. Here I'm using the end, the 0 mark of the ruler. And then you look where the other end of the paperclip lies on the ruler. And note, in this case, we don't have a readout that we can just record. We have to do an estimation from the ruler. So if you look, we're clearly past 1 centimeter and not to 2 centimeters, so it's going to be 1 point something. And we have divisions in tenths of a centimeter, 1.1, 1.2, 1.3, 1.4, etc. So we're definitely more than 1.3, but less than 1.4. And then in this case, you can estimate what fraction or percent of the way the end of this paperclip is between the 1.3 and the 1.4 mark is. And I would say it's maybe 7/10 of the way, or about 1.37 centimeters. Now, of course, you might get 1.6, somebody else might, 1.36, somebody else might get 1.38. That last digit is estimated, and it might have a little uncertainty depending upon how good your measuring device is and how good you are at estimating. But you would report the 1.37. You wouldn't just say, it's about 1.4, close enough. So that is the length of the paperclip. A little bit of a summary. Note that whenever you do an experimental measurement, there's going to be some degree of uncertainty. And that's going to depend upon what measuring device you use and how good you are at using it. So whenever you make a measurement, each known digit in the measurement is what's called a significant figure. The last quote-unquote known digit is going to have a little bit of uncertainty, and that's your last significant figure. So in the case of the paperclip, that would be the 7. The 1 is known for sure, the 0.3 is known for sure, and then the point something 7 is that 7 is a little bit estimated, but it's still reasonably well known, and so we record that, and this would be a 3 significant figure number because the 1, the 3, and the 7 are all results of measurements, so they're all significant. Okay, little practice with this example. How many significant figures, or we often say sig figs, in each of the following measurements? And think about it a moment, and hopefully you would say 3. The 1, the 7, and the 4 are all results of measurements. 160.70 pounds, how many sig figs there? And the answer is 5. The 1, the 6, the 0, the 7, and the 0 are all results of measurements. The 0 here and the 0 there, that's what the device, the scale, let's say, said. And especially this last 0, wouldn't have been written unless it was measured once it's past the decimal place. And then how about this one? How many significant figures here? And hopefully you will say 2. Note that zeros before the first non-zero number are not significant, they're only placeholders. So these are not results of measurements, but this one is and that one is. So that's a 2 sig fig number. Okay, now, what if we have to do some calculations with some measured values? Well, we always have to round off our calculated value to the correct number of significant figures. And that's going to indicate the precision and maybe the accuracy of your overall result that came about from some measurements. There are some simple rules, and it's worth noting that in general, the rule is always you round your answer to the precision of your least precise measurement or quantity that you used in the calculation. But how we do what's least precise depends upon if you're multiplying or dividing. So for multiplication and division, we round to the least precise value, which is what we always do. but in this case it's going to be the smallest number of significant figures in your original numbers. So here's an example. Let's say that we measure a length and a width and we want to calculate an area. 3.285 centimeters is the length and 7.4 centimeters is the width. Well, we multiply those together, we get 24.309 stuff on your calculator in square centimeters. What should we round this off to? Well, this is a 4 sig fig number, this is a 2 sig fig number, so we're going to round off our answer to only 2 significant figures. Note, we don't truncate, we round, but here this is 3, which is going to round down, so we're going to round this to 24 centimeters squared, a 2 sig fig answer. Now how about addition and subtraction? Well, again, we round to the least precise of our original measurements, but here for addition and subtraction, precision is dependent upon what decimal place you measure to. So we're going to be rounding to the least precise or largest decimal place in our original numbers. And hopefully an example of this will help a bit. What if we have 35.3608 minus 32.43? What's the result to the right number of significant figures? And here's a way to look at this that I think is helpful. Notice our first number, 35.3608, has 6 significant figures, but the key thing is this is precise or measured to the 10,000ths place. This one has 4 significant figures, 32.43, but it's known to the hundredths place. And that's going to be what matters. When we do our subtraction, the calculator will say 2.9308, but we only really know this result as precisely as the hundredths place. Everything past that is really pretty, well, it's unknown once we add the two together, because we really didn't know the thousandths or 10,000ths place in that second number here. So we're going to have to round this off to the hundredths place. And again, we round, not truncate, but we get 2.93. And notice we had a 6-digit number minus a 4-digit number. It ends up rounding off to a 3-digit number, 3 significant figures. So the number of significant figures doesn't matter, it's the place. We know this to the hundredths place. Okay, for mixed operations, like let's say you have some multiplication or division and some addition or subtraction, then you do the normal mathematical order of operations and then follow the rules for each mathematical step in terms of your significant figures. So for the multiplication or division, you round to the least number of significant figures. For addition and subtraction, you round to the place, least precise decimal place, and you just kind of work it all the way through. Okay, now what if you get a physical quantity measured or given to you, and it's not in the units you would like, it's not in the quote-unquote right units? Well, physical quantities can be converted, of course, from one set of units to another using what's called several different names, the factor label method, unit conversions, dimensional analysis, and it's all going to be pretty much the same thing. You take your initial quantity, the thing you're starting with, you find the appropriate conversion factor or conversion factors, you might have several of them, that you multiply by to convert from the units you start with to the units you want, and then eventually you get the quantity, the result, in the units you want. These can be really easy, converting feet to yards. They can be pretty challenging with multiple conversions, and we'll do a couple examples here on this screencast, and then more complicated stuff perhaps, or things you have questions on in class. So here's example 9. A blue whale weighs about 700,000 kilograms. How much is this in pounds, in case kilograms don't make sense to you and maybe you can visualize pounds better? Well, of course, to convert from kilograms to pounds, you need to know how many kilograms are in a pound or how many pounds are in a kilogram. And in many cases, you might just know the number because you've used it enough. In other cases, you may have to look it up. So I looked at an appropriate table here, and a kilogram is 2.205 pounds, or a pound is 0.454 kilograms. All right, so what we typically do is we say what we know for starters is it's a 700,000 kilogram blue whale. And then we would like to convert from kilograms into pounds, so we need to have kilograms on the bottom and pounds on the top of our conversion factor. And you could use either one of these. I'll choose to do that 1 kilogram is equal to 2.205 pounds. You could have used this one instead. In this case, you would have had on the bottom 0.454 kilograms and on the top 1 pound. Either case, you have to have kilograms on the bottom, so it'll cancel. And worth noting, this is our original quantity. And this is our conversion factor. And the key thing to note about the conversion factor, and we may have several in some other problems, is that the top of it, 2.205 pounds in this case, and the bottom, 1 kilogram, mean the same thing. So essentially, this is like multiplying by 1, which is because the top and bottom of our fraction are the same, and multiplying by 1, of course, doesn't change what you have. So, kilograms will cancel. We'll multiply 700,000 by 2.205, and we'll have units of pounds. And what this gives us is, the calculator will punch out something like 1,543,500 pounds. And then, of course, you don't want to report that as an answer. That's ridiculously precise. 4 significant figures here. This is 1.000, so lots of significant figures there. But the 700,000 was reasonably approximate. And it's hard to tell with a number like this just how approximate it is. But I'm going to say that whales are pretty variable in weight, depending on how big they are, duh. So this, I want to say, is probably just an estimated 1 significant figure number. So we're going to say that our answer here is about 2 million, or 2 times 10 to the 6th pounds. Of course, if we knew the weight more precisely, we could get a more precise answer. Okay, one last problem on this screencast. Example 10. The volume of the Shasta College swimming pool is about 970 cubic meters. How many liters is this? Well, once again, what we will do is we will start with the 970 cubic meters. That's the known quantity. We're going to want a conversion factor, possibly more than one conversion factor, and we want to ultimately get to an answer in liters, starting with cubic meters. So we need to know things like, how are the two related? And you may or may not find a direct conversion factor, but you can often piece it together from others. So you can look up and find that 1 liter is the same as 1 cubic decimeter. And then a decimeter is a 1/10 of a meter. And we can tie these two together by noting that we can convert from meters into decimeters using this factor, and then from decimeters cubed to liters using that factor. So here's how this would work. If we put that 0.1 meter is equal to 1 decimeter as our first conversion factor, we have meters on the bottom, which will cancel, decimeters on the top, which is going to help us get ultimately to liters. But do note, you got to be a little careful, this is meters cubed. That's meters. So, how do we get meters cubed? We cube something. But of course, we can't cube the bottom of our fraction without also cubing the top of our fraction, or else it's no longer an equivalence. And so we have 1 decimeter cubed on the top and 0.1 meters cubed on the bottom. And a decimeter cubed is a decimeter times a decimeter times a decimeter. So that's still 1 decimeter cubed. You can write it this way. But a tenth of a meter cubed is a tenth of a meter times a tenth of a meter times a tenth of a meter. So you have actually 0.1 cubed as well as meters cubed. So this gives you 0.001 meters cubed as what the 0.1 meter in parentheses cubed means. So you have to be kind of careful there. Okay, now we have meters cubed here, cancels meters cubed there. We've converted to decimeters cubed, and we got a little bit lucky here in that 1 cubic decimeter is equal to 1 liter. So that's just simply going to convert decimeters cubed into liters, and there's no change in value. And if we calculate this out, what we get is 970,000 liters. And most likely we know this number. Probably the 9 and 7 are measured, but the zeros probably just not actually measured. Hard to tell because of the way the number is written, but I'm going to say we have a 2 significant figure value. Therefore, we will write our result in scientific notation as 9.7 times 10 to the 5th liters. And that's our result. So that's it for this screencast dealing with measurement, significant figures, and dimensional analysis.